Well, let's start talking about the material. Anybody got any questions before I start up stuff I want to do? I want to talk about trigonometry today. I'm also going to talk about, um, I'll always be talking about logic as we go along, and I want to talk something about sets today as well. Um, I'm presuming now you have a uh, screen up now that talks about trigonometry. And the page I have it on is page 5 um, and 6. And because I have it on the top here, there are 4 very important formulas that we will use lots of times in calculus. And they're the 4 most important. And the nice thing is they reduce to 2. So there's 2 most important, except the 2 are 2 times 2 in a way. We'll see what I mean by all that in a minute. Anyway, if I think of the cosine of the difference of 2 angles, it turns out there's a formula for that. No matter what the angles are, you can replace that idea. So if I want to say, what is the cosine of 15 degrees, suppose, I could write 15 degrees as 45 minus 30 and use this rule. And the answer would be, in that case, it would be the cosine of 45, the cosine of 30, plus the sine of 45 times the sine of 30. And if I could figure out those 4 numbers, I would know what the cosine of 15 degrees is. In all your calculators and computers, we use these formulas. What happens when you program a computer, and I was involved in this some time ago, when you create a cosine function in a computer, you only compute things between 0 and 15 degrees. Everything else you use these formulas to translate. That's because trig is so interrelated. So we only have to store stuff that's a few degrees, and then we use these formulas to do everything else. And what I just said to you a minute ago was backwards, because I said, suppose you wanted to know the cosine of 15, and you don't know what that is, but you do know 30 and 45 maybe. And so you use this formula. You must learn this formula, and you must learn it correctly. There's a minus on it's a difference, and there's a plus over here. Please get that right. Now,
Is that is that x minus 3 or what?
I'm sorry?
Is that x minus 3?
X, I don't know.
Cos is it cos? What is that? I cannot see that. It's too small.
Okay, can you make your screen bigger? I can't make it bigger for you.
Nope.
It
Oh,
says
there we go. There we go. Now
it's
now it's working.
it's the cosine of alpha minus beta, where alpha and beta are numbers, because this is going to be in radian measure. And that equals the cosine of the first angle times the cosine of the second angle, because they're numbers, plus the sine of the first angle times the sine of the second angle. I'm using function notation. So instead of F here, I have COS, and instead of instead of another letter, I have sine, S-I-N. We're going to practice this a little bit, but this is the formula you got to learn. Now, I prove it. Right now, I'm not so worried about the proofs in here, but you need to try to understand how this is true. It comes from the law of cosines. But right now, I want to emphasize what it says, not how you prove it. But you guys ought to be going through and try to understand what I'm doing. The more you can study what I'm trying to do, the better you'll understand it. Okay? So what I want to do is go to the sum. So this is the second of the formulas. The cosine of the sum of 2 angles is the difference of these things. And when you look at the 2 together, you'll find out that when you have a minus here, you have a plus over here. When you have a plus here, you have a minus over here. And you have cosine, cosine, and sine, sine. So that's what humans got to remember. When do you put a plus? When do you put a minus? And it's cosine, cosine, sine, sine for cosine, because a little bit later, when you do the sine, it's different. The sine of the sum is sine cosine plus cosine sine. That's just enough different to be nasty. Okay. So um, this is, I'm trying to do something to another screen. So you need to learn this formula as also, but notice I'm gonna mess you up here a little bit by moving. The proof of the very first one took this much space. Once I had that done, to do the sum takes one line. The reason is you write the sum as the difference and the additive inverse, the minus angle. So I change the sum to the difference, and then I use the difference formula. In other words, I put the first angle there and there. I put the second angle there and there from the formula up above. I don't like doing that to your head here, but this formula I just used to do this. So I proved this one by using the minus one and other properties. The cosine of minus, cosine is an even function, we said right at the end yesterday. Even function means I can replace this thing with this thing. The sine is an odd function. So I need to replace the sign with minus the sign. That's where the minus sign comes that I have the cursor under right now. So this proof is much easier because we already have something proved that helps us. In fact, we have three things proved that help us. We have a difference formula, we have a even cosine and an odd sign, which allows us to quickly get the result. You need to learn the result cold, I mean well, okay? You need to know how to apply it. Then from that, we get some cofunction relations. If I have the sine of pi over 2 minus theta, it's the same as the cosine of theta. And what you're going to learn once we see how to graph them is that one graph is sort of delayed. They look the same except one of them starts at a different place. We'll talk about that, all that later. I want to talk about this one. Notice for the sine, why did I go do the cofunction things here up at the top? Let's look at the bottom here. How do I prove this one? I changed the sine to the cosine by this rule right here. Okay, this rule right here. I beg your pardon, this rule right here. The sine of alpha plus beta is the cosine of pi over 2 minus alpha plus beta. That's what this says down here. And once I have that, I can write this as the difference of angles using the cosine formula, which I do. I get the cosine cosine plus sine sine. Then I use the cofunctions again to get this formula. So these last two little proofs, I think you're able to much better to understand than that first long one. But I'm hoping you'll begin to see how we're starting to do things, how we're starting to verify things. So if you forgot this formula, but you could remember how you did it, you can produce the formula. So this third formula comes from the cosine formula. The cosine formula comes from the cosine formula. And now we have a difference. The difference one's going to come from the plus formula here. So we first did the cosine of the difference, and then we did the cosine of the sum. We did two cofunction things, then we did the sine of the sum, and from that we did the sine of the difference. In trigonometry, we're not going to use this very much in calculus, but we do have something called the law of sines, and basically you can just remember where it is, and when we need it, you'll be able to use it. And so that's what I wanted to say about that. Now, in the book, in Appendix D, there's a bunch of other formulas. And sometimes students think it's overwhelming, but it's not. Look at it the following way. We have what are called double angle formulas. Okay? Now, a double angle formula means I have two angles, but they are equal. I have a formula for the cosine of the sum of two angles. I have a formula for the sine of the sum of two angles we just talked about. Therefore, I automatically, without doing any work, have double angle formulas, so-called, because the sine of 2 alpha is the sine of alpha plus alpha, and we know what the sine of alpha plus alpha is because we just did it. what it comes out when you simplify it. So I'm going to go back up here a little bit, probably making you dizzy. You have to get above the sign thing here. If I think of alpha and beta are equal, if alpha and beta are equal, what happens? This becomes alpha plus alpha. This becomes sine alpha, cosine alpha, plus cosine alpha, sine alpha, all alphas. Here I have sine alpha, cosine alpha. Here I have cosine alpha, sine alpha. Those are equal. That's two of them, and you get this formula. So if you know those first four formulas, or the first two, as I told you, you can figure out the sign of the sum of angles if they're equal by using those first formulas if you forget. Now, most of us use this enough that we learn it. But the sign of the sum of two angles is easy if they're equal. It's just twice the sine times the cosine. The cosine is harder because there's three different ways to look at it depending on how we want to think. So for the cosine of the sum, it actually, when you do cosine, cosine minus sine, sine, why would you do that? Because this is alpha plus alpha. So that would be cosine alpha minus sine alpha, which is cosine squared. Now, with trig, we put the square inside here instead of outside. That can sometimes get us in trouble, but that's what people do. Now, if I use a Pythagorean theorem, I'm hoping you remember the Pythagorean theorem. That says the sine square plus the cosine square is 1. If I replace the sine square with 1 minus the cosine square, I get 2 of them minus 1. On the other hand, if I replace the cosine square with 1 minus the sine square, I get this formula over here. You need to learn for the cosine of this, of what's called a double angle formula, you need to learn all three of these. But if you know one of them, you can get the other two from the Pythagorean theorem. Pythagorean theorem says sine square plus cosine square is 1 no matter what the angle is. Now, there's these last two formulas are where people mess up problems on the test because they forget what a half angle formula is. Now, you don't want to forget, you just want to remember the following thing. All you do with a half angle formula is take a double angle formula and turn it around. What do I mean by that? Here's the sine square. Here's 2, here's 1 minus cosine. If you look up above, where do you see sine square, 1, cosine, and 2? Well, you see it here, and you see it right here. I see something else, by the way. You guys are not awake. There's a mistake in this formula. Do you see the mistake?
Maybe it should be 2 sine squared.
There should be a 2 right here. That's a typo. Now, that's as far as I know my first typo. You guys need to find these typos. When I go through it, just like you'll be going through it, this doesn't make any sense. You don't know it doesn't make any sense because you haven't done it yet. That's why we do a proof. When you do a proof, you won't get this. You'll get this one. This is correct right here. This one's correct. So it's correct all the way over to there. I just noticed this one's wrong. How do I notice it? I'm trying to prove this, and there's a 2 here. If I multiply this 2 to both sides, I'll get 2 sine square. I'm pointing at, it's funny. If I'm in class, I'd be pointing at something. I just pointed at the screen like you can see me. You can't, okay? So I'm trying to explain with my hands, and I'm not in Italy. In Italy, you explain everything with your hands. Anyway, so there should be a 2. Does everybody see that? In the notes on Blackboard, this will be changed so that the notes you will have to read by tomorrow will be different than the notes, because I'm going to delete the note in Blackboard that's this material, and I'll put the corrected version in, okay? So if you printed your version that's going to have a mistake in it, you need to put a 2 right here on page 8. Other than that, you'll be wrong. Okay, so assuming that you see a 2 here, If I would take this to the other side of the first argument and take the cosine, or just leave it alone, let's say, take -1 instead, I write that as cosine 2 alpha minus 1, then I'd have minus that, minus 2 of them. Multiply by -1, I'd have this right here, and divide by the 2, I'd have this. So if you just take this formula written correctly and equate it to that and rearrange it, you'll see that this is true. So if you forget a half angle formula, but you remember a double angle formula, you can do it easily. And the cosine one, this was correct. The cosine proof right here requires this right there and this right here. You add 1 to both sides and divide by 2. That's what this says. Add 1 to both sides, that's there, divide by 2. So these half angle formulas, notice why do they call it a half angle formula? Because that's alpha and that's 2 alpha. Why do they call this a double angle formula? Because that's 2 alpha and that's alpha. Okay? Now, the last one, this is the one people learn least, and it's too bad, but they do. The product of sine and cosine can be written as a sum, and the product is so there's 3 different things you can do here if you have products of these things. And when we do integrals later and things, we will need to know these formulas. These aren't used as often, but they are used. So what you need to have is some place where you can look these up fast. One place is in Appendix D. The other place is in this handout, which will be on Blackboard, hopefully corrected by a little bit after the class today. Has anybody found any other typos? Has anybody read it? Same response. Anyway, okay. Well, by the way, if you don't want me to make these notes because you don't want to read them, I won't make them. It'll be a little more difficult for you because you'll have to figure out this stuff for yourself.
No, I read them.
Okay, good. Because it takes me a lot of time to do this, you guys. And if you don't appreciate it, I'm just going to take them away from you because I'm a mean person.
Dr. Brady, I have a question again.
Yes, please.
Okay, so for I guess I'm asking, like, for these formulas,
Yes.
will we generally know which formula to use, or will it state in the problem which one we need to use?
Sometimes, yes, no. I mean, it's hard to answer in one answer. Basically, if you have a situation, I'm just using what's on the screen here. If you have a situation that you come across and it's got 2 alpha in it, if it does, one of the things you think about, not necessarily do, but one of the things you think about is, hey, maybe a double angle formula is going to come in here. That doesn't mean you do it, but it comes to mind. Like if I say 2/4, you probably think 1/2. You might not write 1/2, but you think it just because you're used to it. And so to answer your question, you basically go along, you see something and you stop and you say, okay, what's that? And this list of formulas, either here or in Appendix D, ought to be like always over there, like maybe I got to go look at that list. So you ought to have all of that ready. Now, once you've looked at the list long enough, once you've tried to look at and understand all this, what will happen to you over the semester is all of a sudden you'll know this stuff. And when a cosine of 2 alpha comes up, you'll automatically think the right way. So I don't know, again, if I'm answering your question, you sometimes have to look it up. Sometimes they'll help you by how they say it. Sometimes you'll sit there and you'll look at it for an hour and you won't know what to do. That's the nature of math. So when you look and you don't know what to do, what you ought to do is sound it out, talk it out, and then call me. And hopefully, and I can say, hey, look at it this way. And then you say, why didn't I think of that? And then again, the next day, if a similar thing comes up, you will think of that. And then you'll be proud of yourself because all of a sudden you can do it yourself. Now, is that an answer? I don't know.
Yeah, that makes sense to me.
Okay.
I do have.
Go ahead.
Okay, I just had another question. When we do have class in person, when you're going over notes like this, will you just like go over them like what you are now, or going to be writing on the whiteboard? Do you know yet?
Okay. What I do a lot of times in class, I'm assuming you guys have access to the notes, which, for example, in class, if you have a phone or a computer or a laptop or something, you might have this up on your page, just like we have it now, like we're looking here. It wouldn't be me sending it to you, for example, but you might, by going to Blackboard yourself when you have your laptop on, you might have this screen yourself sitting at your desk, okay? So you could see the screen yourself. Now, second thing is, when I'm in the classroom, I can put stuff on the screen just like now. Except those of you sitting there would wonder why I just don't write on the board. But we can do similar things to what we're doing now. It's just not as nice here because I spent a month setting this up. Okay, it may not be good enough. You may think, boy, that's a wasted month. But if you see what's in the classroom, you'll see why this is better. Anyway, now what I do on the screen or on the board a lot of times is try to explain. Like instead of me doing this stuff with the cursor right now, this stuff I would write out and show you how to do it. Okay, so what I do is I react off of this kind of thing, like how do we do this? I write out the proof for you on the board. That's not in these notes. So the in-class sort of augments what this stuff is. This is what you guys are supposed to read ahead of time and study. And then the classroom, when I'm with you and I can see you and see when you're understanding and when not, I can try to say, okay, let's cover this a little bit more or this a little bit less. And I use the Blackboard to try to explain the things that you guys don't understand. Now, if you haven't read the notes at all, then I cannot write on the Blackboard as well as I am printing here. The printed notes here is what I would love to be able to write on the Blackboard to show you. But writing just this page right here would take 10 minutes on a Blackboard. And we only have 50. So I use the notes for you to have something that's correct and well written, hopefully. And then I use it when I'm in class, I try to interact with you guys to try to get you to understand what's in these notes or what's in the book. Now, again, I apologize for these long explanations, but I hope it helps more than just the person who asked the question. Because sometimes the rest of you have questions too. Did that help?
Yes, it did. Thank you.
Okay. And part of it is we're going to have to experience the class. And some of you may think, I don't want to do this anymore. Let's go back to remote. And others of you think, oh, this is much better. We don't know yet. We're going to have to experience that together. I don't know if I want to stare at you guys either. Okay. And again, as you'll get to know me, you'll know I try to be humorous all the time. Okay. So this is essentially the end of these trig notes. Anybody got any other questions besides a couple of people that's asked? I mean, you can, how are we doing? Because I want to go to something else. And to do that, I need to go to a different thing here. That's kind of a shocking thing to see on my screen. But Kenzie's got a picture that I see. I don't know if you guys see it or not, but I guess you see me, don't you? Now I see Kenzie. Oh, no, that's not Kenzie. Anyway, who cares? I'm going to share the screen again here for something else. Okay. The next topic that we want to talk about is to talk about what are called sets, real numbers, and things, and functions. The functions is what the book starts out in section 1, as you know. So what I'm doing here, as you'll see, is I first just say, this first few paragraphs is just a review, real quick review of 23 pages that you did with logic. A mathematical statement is a sentence either true or false, but not both. Mathematics only deals with mathematical statements. A theorem is a true statement. A proof is a demonstration that the statement is a theorem. Much of what has been done in the 100 last years has been called based on set theory. So we got to talk about that because everything we do is going to involve sets. Now, I'm going to kind of read this in case you haven't, but I don't like to just read to you, but I'm going to in this case because it's very important for you to get the right idea. A set is a mathematical concept consisting of an identifiable collection of objects. Now, those are not math words, those are explanatory words. So I say I have to try to explain it because I'm in math. The last sentence should be understood to be an attempt to provide a characterization or description of the concept of a set and is not meant to be a mathematical definition. It's meant to be like a dictionary description. The objects may be anything whatsoever, and the collections may range from collecting no objects to collecting a large amount, and that includes an infinite number. An object that is collected is a member or element of the set. All right, we have symbols for that. So I say in order to avoid certain logical inconsistencies, see all these big words I get into when I try to explain things, we shall assume that for a collection to be a set, the collection must itself be a member of another identifiable collection. That will be clear later. The symbol for set membership is this weird looking E thing. It's not an E thing, but it looks a little bit like an E. If it is true that little a is an element of a set, let's say denoted by capital S, then one writes A and this symbol and S. The symbol is read member of or element of. So when I see this A, sort of a horseshoe thing with a line and an S, I say A is a member of S or A is an element of S. So I read that symbol as a member or element. If I don't want it to be a member, I cross out that epsilon, and it's not epsilon, but some people call it epsilon. That's the fifth letter of the Greek alphabet because epsilon looks more like that than E does. But actually it's not epsilon because it's actually a letter in the Swedish alphabet, and you don't care about all that. I am full of worthless pieces of information, okay? So, no set can be a member of itself. So what I write here, right here in this place, right here, S is a member of S is always false, no matter what S is. The word identifiable is not defined here mathematically. We shall see that not all collections are identifiable, but I got to get someplace before we do that. Elements of sets are capable of possessing properties or having relationships with other elements of the same or different sets. Properties and relationships are mathematical statements featuring elements and sets and perhaps other symbols. It should be understood that if a property of an arbitrary element of a set is stated, it is not to be concluded that the property is true for every element of a set, but only that the property has a meaning. So we may not know the answer, whether it's true or false, but it is either true or false. Like you may not know who won the World Series last year, but you know somebody did. Okay? And so a set's called well-defined if it is clear what constitutes its members. Now, that's an ambiguous statement because to whom is it clear? So when I say it's well-defined, that means it's clear to me. Okay? Unfortunately, books sometimes tell you what's clear and it's not clear to you at all. That's just the way it is. So what you have to do when you see some idiot statement like it's clear is remember it's clear to the author. And what the author is trying to tell you is, if you're very smart, you ought to figure it out. Well, that's a put down. Authors shouldn't do that, but they do it all the time. That's why sometimes I have complaints about books. Okay. Now, here's the first example, if you're all still awake, of what subset is. Now, we know what a set is. That was that identifiable collection of objects. What do we mean by a subset? Now, we have a symbol for that. When we write S and this horseshoe and T, that is read, R-E-A-D. S is a subset of T. That's how you read it. It doesn't mean, it's not what it means, it's what it says. What does it mean? Here's what it means. And here's our first example of why I tried to show you some logic. In order to understand subset, you have to have a quantifier and you have to have an if-then statement. What it says is, for any object whatever, If it is a member of the set S, then it's a member of the set T. Now, I'm hoping when I say it in English, you understand what I'm saying. If I'm a member of S means I'm a member of T, then in a certain sense, T is the bigger set. We haven't defined big, but the point is, subset means a part of, okay? But I just can't define as a part of because we didn't have to define part. And we're trying to define as little as possible. And so all I need to do here is define the element twice, define if then, and define the quantifier. This is how math is done. Okay? And it's a simple statement. It can get maddening a little bit, but it's a simple statement. Now, when are two sets equal? Well, the definition for equality of sets. Now, what do we write? We write an equal sign. You know that equal sign, but now we're talking about sets, not numbers. Two sets are equal when they are subsets of each other. So if S is a subset of T and T is a subset of S, when that statement is true, we say they are equal. So sometimes we want to prove two sets are true, we have to prove two parts. We have to prove the left is a subset of the right and the right is a subset of the left, sometimes. Okay, and it's an and statement. Okay, now if the collection is small, we may be able to describe it by just describing it. Namely, if I want to talk about the set with elements A and B in it, I can write this. There's no order here because it's the same collection. What does this set have in it? A is an element and B is an element. What does this set have in it? A is an element and B is an element. So you could quickly show those are equal sets. They have the same elements. Okay, now, what if you list an element twice? Well, I'm going to prove to you that they're the same set. So let's try. If I take something in the left set, what is it? A. Take something out of the left set, it's A. Is A in the right side set? Yes. So this set is a subset of that set. Take something in the right set, that's A. Is it in the left set? Yes. Therefore, this set is a subset of that. So when you repeat yourself, you're not changing the set. It's still, this set, even though it looks like it has two members, is actually only got one member. When you write it this way, you're trying to confuse people. Okay, so some stuff like this, that when you have notation, you have to know how to interpret the notation. And sometimes the notation fails you because when you see something like AB, you think they're different. But if they're the same, you don't really have two elements in the set, you only have one. This is called a singleton set. And by the way, this is also a singleton set. Now, another way to describe sets when they're more complicated is to use a statement to describe them. So if P of X stands for a mathematical statement featuring the letter X, where X is an arbitrary element of the set, then this symbolism, I'm going to read it to you. I'm going to read it as it goes. This says the set of all X, the straight line vertices such that X is a member of S and whatever the statement P of X is. Or sometimes we collapse this a little bit and say the set of all things X is a member of S such that P of X. So we might be saying the set of all numbers greater than 4. And P of X would be X is a number greater than 4. Okay? So I go ahead and I explain some more, and I tell you in words here what I just said in my voice. And down here is that all need not concern us much for current purposes. If you leave the set S out, you can have some logical difficulties. We'll talk about that kind of stuff later. Now, this is our first statement. Suppose P of X is the statement X equals X. Then what is this set? The set of all things in S such that X equals X, that's just S. All the things in S that are equal to themselves is just the same set. So this is just different ways of saying stuff, okay? Now, suppose we have the statement, and this gets logically much more difficult. Suppose I have the statement X is not equal to X. So what things do you have that are not equal to themselves? The answer is, this is always false. Okay. There's nothing in this set. It's called the empty set. It's a set with no elements, and this is how you define it. It's the set of all things in a set where the number is not equal to itself. This defines no objects. And it's important in math that we have a set that has no objects. Now, those of you who like to shop, my wife likes to shop, for example. Sometimes she'll go shopping, she'll spend the whole day, and when she comes home, I'll say, what did you buy? Oh, I might say, did you enjoy yourself? She'd say, yeah, I had a good time. I say, what did you buy? She said, nothing. Well, that's how my wife and I are different. I don't enjoy going to a shopping center and buying nothing. I go there to buy something. But my wife is purely happy just going and looking around. Okay, you may be the same way. Lots of people are. The point is, what she brought home is the empty set. What she brought home is an empty sack, is something with nothing in it. If she brought home a box, it doesn't have anything in it but the box itself. Okay, and if we're talking about what's in the box, then the box is just it's just the brackets around the thing. You didn't have anything. So an empty set's like an empty box. Okay, now here is one of our first hard statements because it's so easy. I'll explain that in a minute. 18 minutes after, so I can't talk too long here. The empty set is a subset of every set. Now, here's the statement for subset, where the empty set is right here. Tell me, is the statement X is a member of the empty set, is that true or false?
False.
False. Therefore, I have an if-then sentence with a false if. If you have an if-then sentence with a false if, the whole sentence is true. So this is a true statement. It's called a vacuous statement, but it's true because the if part's always false. But this is a statement that says that the empty set is a subset of every set. Okay? And then there's some more stuff here, but we're running out of time. So I'm going to cut off of this. I'm going to get out of this thing so you see me again. Hope not everybody's asleep. Hope you've been a little bit awake to hear this. Anyway, I'm going to kind of piecemeal myself through Monday since we're going to come back to this room. You guys will come back to the Zoom session. I'm going to keep going through this stuff. I hope you try to study it yourselves first. And I would love it if you would tell me on Monday, I can't read page 8, or I can't see the second paragraph in page 11, or I'd like to know where it is you can't understand. Because if you don't ask me, I'm going to assume you know. Now, I actually know you don't know. But for class purposes and grading and stuff, I got to assume you do know if you don't ask me. So if you fail because you don't ask, that's not my fault. Now, I'm not really a mean person. Well, I kind of am. But what I'm trying to say to you is please study this stuff. It is not easy to understand. But if you spend time doing some of this now, you'll be surprised how easy the whole rest of the class is. Because the book is much less deep than this. And so when we go through the stuff later, once I get through these notes, we're going to be going back to the book. That's going to get much easier. But the time you spend right now will pay big benefits to you later. And you don't have to believe me, but I don't care. I get paid a lot more than you do. I know what I'm talking about. and I get paid whether or not you like me or listen or read the book or anything. Anyway, I'm just kind of kidding with you now. But what I'm trying to say is, please study. And anybody got anything to say? Any complaints, problems? Anything that comes up, like you can't get on WebAssign or something else happens, email me. Oh, one other comment before I lose anybody or too many of you. I am not like you in the sense that I do not text all the time. I don't stare at my phone all the time. I love to turn my phone off and work myself by myself for hours, 24 hours sometimes. So if you write me at midnight, I may not be looking at it. If you write me at 3 in the afternoon, I may not be looking at it. So if you need to get me, call me, because the phone rings and I know you're trying to reach me. Okay? But sending me an email message, I may or may not answer it. Now, during this pandemic, I'm staring at my emails a lot more. It used to be 2 or 3 days before I look at emails sometimes because I'm very busy. I'm very busy because I'm very incompetent. Okay? And so, anyway, you can think that if you want. So I'd ask you if you need to get with me, like I need to get this thing done, and then the deadline's at midnight, and it's 11 o'clock, and say, call me. We'll fix it. If you email me, I may not see it till 2 days later. Everybody kind of understand? I want you to communicate, but I don't want you to say, why didn't you call me? Well, it's because I haven't seen the message. Okay? Okay, well, thank you for listening. Unless you want to say something, you want us to stay after, I'd be happy to talk to any of you in a little while. And otherwise, have a great weekend. If you can have a great weekend in the pandemic, I don't know if you can or not. I will. And I'll see you on Monday. And I'm going to continue these notes. You got some more notes. I may be putting more up because I tend to do that. Okay. So I'll see you Monday.